So I want to talk about this safe arithmetic library that we're working on at Intel. Um, but before I do that, I want to let you know who I am. So I'm a firmware architect at Intel. I've been doing C++ not too long, since about 2020, so 3 years. Um, and I develop power management firmware for our power management controller in our chipsets. Work with a really awesome team, including Ben, Dean, and Michael Case. They're pretty fantastic. Um, yeah, I enjoy what I do quite a bit. So, what problem are we trying to solve here with safe arithmetic? And this is something that, there's actually quite a number of other libraries that work on solving this problem in different ways with different strategies. But the root of this problem is that our C++ integral types are really just a subset of all integers. So not real integers. Um, and that causes some problems for us. And this isn't unique to C++. Really every language has this. Even if you have something like big integers, ultimately, you're going to run out of memory. So there's really a subset here. Um, and we all know this. The values that we can represent an unsigned integer is 0 up to the power of 2 of the width. It's about 4 billion for a 32-bit unsigned integer. Unsigned, we lose half the maximum value, but we gain that in negative values. So our actual operations that we're doing for unsigned arithmetic are modulo arithmetic for the most part. For signed arithmetic, we don't actually know, because if you overflow, the behavior is undefined. There's a lot of different behaviors the processor might do, the implementation and the processor might do. So it might saturate on a DSP, for example. It might wrap around, but it might wrap around at a different size than what you would think it would wrap around, or it could trap. Right? There could be a hardware exception for it. And an interesting thing that I found out while implementing this library is that the percent operator is not actually the same as the mathematical modulo, specifically for signed. So that was a fun one to discover. Python implements it one way. C++ implements it a different way. So I had a little script in Python to help me figure out some of these things. Yeah, these are the different options that we can have. Yeah, and the fourth one is really the scariest one. It might just be completely optimized out. So we really want to avoid overflow in general. So how do we resolve this? What are our options? Well, the first option is the one that we all do today, um, and we can just ignore it. And the benefit of this is it's really easy to do, and as long as we don't run into any problems, it's great. The problem is eventually something's going to break, and when it breaks, it's pretty catastrophic. So who implements this? All of our beloved C++ integral types do this, and yeah, it's fine for the most part. And then it's not. Um, Theric 25 was a radiotherapy machine that was, I think, the first machine that was very, very computerized. So it had an 8-bit processor in it. It was not programmed in C++. But an integer overflow caused really serious damage to people, including deadly radiotherapy doses. Just an integer overflow. Well, and several other bugs that it also had. Boeing 787s had a computer crash where there was 2 different integer overflows requiring the the interim solution was basically to reboot the computer every so many days, but it could lead to misleading information being displayed on cockpit displays. So then the recommended method by lots of different safety standards is to check for overflow at runtime. And this is a accepted safety critical practice. The con here is you have to know what to do if you do overflow. So in all the cases where you might actually overflow, you need a plan. If I do overflow, how do I recover from that? Do I recover? Can I just terminate my program? What are my options? Sometimes you can't just terminate your program because you're controlling a rocket. And if you just terminate, that will cause problems. But there's a number of libraries that implement this, um, including Boost's safe numerics, which has options for runtime checking. It does more than that. Um, and these are just for C++. There's C libraries, macro libraries, all kinds of fun things that really make writing safety critical arithmetic kind of a pain. So I didn't have that picture of a rocket on accident. Luckily, that rocket was taking the James Webb Space Telescope to L2, and that went fine. That went great. But a previous flight had an integer overflow, and it was detected, and it was caught correctly. But you have to know what to do to handle that exception when it occurs. And I say exception, whether it's a C++ exception or it's just some error code that gets returned, it doesn't really matter. It's just some exceptional error case. And so this caused the destruction of the rocket and its payload. So it did the right thing in catching the overflow, but handling it can be difficult. What we really want is to pretend that C++ integers can be real integers. And so how can we work in a space where that's true? One of the options is something like a big integer or arbitrary precision integer. So you just let it grow. Performance is much worse than primitive types. With a primitive type, adding two values is usually just a single machine instruction. Even if you're adding 32-bit values with the arbitrary precision library, you can't just use one instruction. There's additional things that you need to do. So it's quite a hit to your performance. And these integer values can still overflow your functional limits. So you might not be overflowing the container that you're fitting in, but the values can actually grow to be larger than what your algorithms and your code expects, causing errors in different sorts of ways. And that's not too great. What we would really like to do to solve this problem, to make our integers behave like real integers, is to have preconditions on our operations. So if we can constrain or we can know at compile time what values we expect each of our variables to be potentially, then we can prove what the output value range can be. And we can do this at compile time. And this actually has a lot of benefits. Major benefit is you don't have to run your code to find that you have an overflow. You can compile your code and you can get an error that says, hey, when you add 0 through 10 plus 0 through 10, there's a possibility it's going to be 20. And that overflows your result, which is expecting, less than 10. But yeah, if we constrain the results to be within our requirements, then we don't get overflow. And yeah, I adapted this from a 5-minute lightning talk at CppNow, which was adapted from a full talk. So it's suffering some compression artifacts here. So who implements this? Well, Safe Numerics does this, and it does it in a pretty great way. And it's a fantastic library for C++ 14. But we have this new library that we're working on called Safe Arithmetic. It takes a lot of the things that are in Safe Numerics and some of the other strategies that we've seen here, and it expands upon it in certain ways, and it also restricts it in other ways. This is a work in progress. I wouldn't use it in production quite yet. But when I do use it in production, I'm sure I'll be fixing quality of life issues and bugs and things there. But it should be considered experimental and ready to play with and try out and file issues for bugs and enhancements. So how do we do this? Well, these 3 points really outline the strategy. One, we want to store our integral values in types that describe the constraints. So this could be a range, could be a set of values. It could even be the union of multiple ranges. But it really just describes what are the possible values that this runtime variable could contain. And then we provide safe mechanisms for creating these values. So we can't create some value that's violating its requirements. And we strongly discourage or disallow safe operations. And it's really strongly discouraged because ultimately you can do any terrible thing that you want to do. But the idea is to make it easy to discover in code review that there's something awful happening that we need to take a close look at. So the first thing we do is we introduce these really basic safe integer types. These are somewhat useful on their own, especially if you're doing some manipulation, like you have an unsigned 32-bit value. You want to extract a bit range out of it, right? The process of extracting that bit range, anding off, bit masking some bits and then shifting them over, that's actually going to constrain the result type as well. So if you extract a 3-bit field out of that, your result type is actually going to be 0 through 7, and it's going to have that encoded in the type. And that's similar to safe numerics. So with this, we also have some UDLs, and these UDLs help the library know, okay, you're assigning 10 to this, right? Or you're assigning 32, and I know that fits within here. So we could add 2 signed 8-bit values and get a signed 16-bit value. So that's nice, but not super practical, because we might have 2 32-bit values, and I know that it's 10, and I know that it's 32, and I know that it should fit within the result. But the safe arithmetic library will complain about this, because A and B are runtime values, even though in the previous line we gave them a compile time value. It's ultimately a runtime variable. So we need a better way to represent our constraints. We can't just use the types. We'll run out of types very soon. And so we have the concept of an interval. And this is also something that's exactly in the safe numerics library. And so we have an integral type A, it's assigned 32-bit integer, and we're telling our code it can only contain a value between 0 and 100. You can't assign anything else to it. It'll fail compilation. And so now we can constrain our A and B types to be 0 to 100, and we can assign that, the addition of those two, to a third type that could be 0 to 200. And we could use auto as well. The library will automatically track the types. So that's helpful. And so this interval is just one part of a DSL. It turns out it's really useful to have more than just intervals. And so this DSL, this is kind of the expanded form of that interval, where we have the type on the left-hand side, and then we have the constraint on the right-hand side. Another sort of constraint that we can have is a set. And this could be for an enum even, where there's only a specific set of values that are valid. And if you try to assign it to something else, it'll fail. Compilation. And there's a shorthand for that as well. The mask requirement is a little bit more complicated looking in the maths expression, but what it really is saying, it's a requirement that's optimized for bit types, like bit operations, where we want to shift, we want to do bitwise AND, bitwise OR, bitwise XOR. And so one part of that mask represents, these are the bits that are fixed at constant values, so either 0 or 1. And then the other part is, these are for the constant values, this is what the value of those constants are. And so our value in Y must satisfy that requirement. And the part that kind of makes it a little domain-specific language is that we can do things like union on these. And so if you can imagine, things like division, well, we don't want to divide by 0 because that's undefined behavior. And so we'd like to avoid that. And we'd like to prove to ourselves that at compile time, our denominator is not 0. And so here, this gives us a small range with 0 omitted. We can do intersections as well. And typically the intersections can be simplified. And so this actually is the full range from minus 10 to 10. So all of this mechanics are only useful if we can ensure that the values getting into our safe types satisfy those requirements. And so if we take a raw integer from some location, doesn't really matter where, and we try to assign it to a safe variable that doesn't fully contain the representable range by the right-hand side, that'll fail compilation. So you can't just do this. That could be a problem. We have lots of libraries that we need to interop with, and also real-world data that we're getting from some external location is not going to be wrapped nicely for us in a safe variable and guaranteed. So I'm going to do a quick detour here. When we perform operations on safe values, we recalculate what is the possible range of outputs. And in this case, it's a simple range. It's an interval from minus 100 to 100, but it can be more complicated than that. We can have disjoint unions where there's multiple intervals across the line. We can have masks. We can have intersection of a mask and a range for more complicated, bitwise and arithmetic operations. But all of the operators are overloaded to support this and to do these calculations, including modulo, which was far more complicated than I expected and probably could be optimized quite a bit more. And then we can do things like min and max and clamp. Min, max, and clamp are also extremely useful for being able to take some external data and massage it into some range that satisfies your requirements. So in some cases, this is actually what we want to do. Like, let's say we're doing saturating arithmetic. Well, just clamp the result, right? Clamp the result so it fits in what you need. But that's not always the case. We can assign safe values to other safe values only if the requirements of the right-hand side satisfy the requirements of the left-hand side. So we can prove this could be 0. 0 is less than 5. This doesn't compile. It fails. One of the other things about the library is you can default construct something if its value includes 0, if its potential value includes 0. If it doesn't, you have to give it a specific value. So all of our safe values are initialized by default. And if you don't have a default value, like if it's not 0, then you have to tell it. Yeah, and the denominator for modulo and division must be non-zero. So a few more ways that we can create our safe values. If we're using something like S64, that actually includes the full signed range of a 64-bit integer. So we can assign, any type to it that is contained within that. So that's fine. We can use these UDLs to assign values. So 42 is it's like an integral constant, not exactly, but it's a similar sort of concept, and we can prove at compile time that it fits in there. So all of this has been compile time. None of this costs anything at runtime, but we still, actually calculating the runtime values, of course, that's a runtime cost, but it's not on top of the calculations that you would be doing anyways. So when we are ingesting information from the outside, whether it's from some network packet or it's from user input or it's from a hardware register, we can't expect it to satisfy our requirements. We really can't have any sort of assumptions on it. So we need a way to take that and check it at runtime. And when we check it at runtime, we also want to wrap it into a safe value. We want to say, yes, this actually does satisfy the requirements for this, and I'm gonna give you a safe value that has that. And so we have this match function, and this match function takes other functions, and it's kind of like pattern matching. It's not exactly, but it's kind of like pattern matching for integral values. And what you do is match returns a function that you can use. And so you can take the function it returns, pass an unsafe value into it, and it's going to evaluate that against the different options within the match function. So this first option here says, if the value is between 1 and 100, then this is valid, and then you can execute this. And so I'm actually I'm doing two things here. One, I'm specifying what A must be, and two, I'm wrapping it into a safe value for you that the type contains that range information. And so we can do anything we want with A, and we can be safe and assured that A is guaranteed to be within that range. And if nothing matches, there's a default function that gets called. So this is something I haven't seen in other libraries, and it's a pretty important quality of life and usability thing. So I have an example here in Compiler Explorer where we're taking a character digit and we want to calculate what's the hex value of that digit, right? And so the way that you might do this is just comparing the digit value. If it's between 0 and 9, then you subtract, the character value of 0. Lowercase a, lowercase f, subtract a minus 10, etc. And so I can look at this and I can review it and I can see, okay, yeah, this is probably correct, right? However, we can do this with safe arithmetic, and we can use this using the match function to generate another function for us that does this. And here, my decimal digit here is guaranteed to be 0 to 9, and I can subtract this constant from it. I can return that. The other case, it's between 0 and f lowercase, and the final case, 0 and f uppercase. And so the library actually takes the return types of these first three lambdas, and these return types, based on these operations here, encode the possible values that each one of those could return. And so 0 through 9, this could return literally 0 through 9. A through F could return the values 10 through 15 and 10 through 15. And what it does is it actually takes all of these and creates the union of them. And so our output type is a safe value, signed 32-bit integer, between 0 and 15. And if we look at the code that gets generated, at least for Clang, also this is ARM assembly. It's the unsafe version. It's 12 instructions. The safe version is also 12 instructions, and it's actually the exact same code gen. And so we're not losing anything at runtime by doing this. And on top of it, when I'm reviewing this code, I can feel very safe down here because it compiles. This is guaranteed to be 0 to 15. This is very, very useful. And like we saw in the example, we can have multiple match options and arguments. So I explicitly chose this pattern because I want to make it hard to do the wrong thing. And if we had a way to check and see if something matches a certain range, we could return an optional, or we could potentially return an expected. But if you do that, you don't have to check it before you use it. It's not like forcing you to check it before you use it. And this pattern, there's no way to access the value in an unsafe way, right? The only way that you get the safe value is by passing it through this match function. So you can't avoid checking it. And this gives us a nice ergonomic interface as well. Sometimes we really do know better. And this is when it gets scary, and it should be scary, because we're going to be doing things that says, you know what, safe arithmetic, I know that this feedback function, even though you can't prove that it's always going to be within these intervals using the safe arithmetic rules, I know that it actually can never exceed this certain amount. And on top of that, I don't want to pay the cost of doing a clamp for whatever reason. Clamp would be a safer thing to do. It would be better. You'd be guaranteed you're not going to go out of bounds. But maybe you can't for some reason. So we need a way to do that. We can't just restrict people. But we need to do it in a way that's scary and obvious and easy to search for. So when somebody else is reviewing my code, they can just do a grep for unsafe. And whenever they see unsafe, they know there's something scary that's happening. And we have to take a really, really, really close look at it. And we have to understand, is this really the right way to do it? Is this really correct? It should almost always be never. Like, we should never do that. But sometimes there are requirements. Yeah. So how do we get values out? And what we're doing here with safe arithmetic is kind of creating a hermetically sealed environment of these safe values. And so we have very clear ingress points where we're making values safe. We also want to have very clear egress points where we're getting a safe value out and we're converting it to an integer. An operator on two safe values in the source code can look the same as an operator on two naked ints, right? So we need to have a very clear indication that we're taking a safe value, we're giving up the guarantees that it has, and we're gonna get a raw integral value out of it. And we do that with a safe cast. We can't implicitly cast. That could make it too easy to lose our safe guarantees without realizing that happened. So we can have a safe cast, which isn't as bad as an unsafe cast. It's always guaranteed to be safe, but it does mean that V, when we start doing operations on it, there's no guarantees anymore. There's no checking. It's all bets are off. Besides the fact that at the point we do the safe cast, it's going to be between 0 and 100, right? And also this will do a check to ensure that the destination can represent the full range. So the int must be able to represent 0 through 100, which is fine. So yeah, this is a sealed environment that we create with our sort of safe context with clear entry and exit points. That's the whole library, basically. There's one additional thing that I didn't cover here, and that's algorithms. So if you try to do just a regular for loop incrementing a safe value, that's going to be a real hassle because you have a value 0 through 100, you add 1 to it, now it's 1 through 101, right? So that's really annoying. The library provides, it's an interface similar to Boost's iRange and Python range, where you say, go from 0 to 100 and give me a value, so you can do a for each on that, and then you have a safe value. Another thing that I didn't cover here, and I can actually probably code this up in Compiler Explorer, is the safe array. So the safe array allows us to just wraps a std array, but we know the size of an array at compile time, right? And so the index operator and the at operator, or the at function, they don't do any runtime checking, but they do compile time checking. So you must have proved previously that your index into the array will not go out of bounds. This is really nice for multiple reasons. One, we already did the check somewhere. We already proved to ourselves that we're not going to go out of bounds, right? So two, when we do index into the array, we want to make sure we don't go out of bounds. We want to catch that if we do, but we can catch that at compile time. There's no need for an exception or an error condition at runtime, because that's already been handled. Alrighty. Thank you, everybody. It's a lot of people early in the morning. I really appreciate it. Yeah. Yeah. So the question is, have I thought of the concept of using not a number to indicate that there was some overflow or some sort of error condition? Yeah, I have considered that. And the problem with that is I'm really lazy. And lazy in hopefully a good way. I if I propagate some error condition, then that error condition has to be checked at runtime whether we've hit that. And so each time we do an operation, we need to check, are we doing that? And then we need to either trap or we need to propagate it. Um, I do have an algorithm for doing accumulate because accumulate is another one of those things where you're accumulating into some variable. And if you don't have nice machinery, it's like it's it's almost not possible to do. And so there's an accumulate algorithm, and that takes basically uh, an array or safe array or some range of safe values. And you give it a compile time value, and you say accumulate up to 10,000 of these. So it calculates what's the maximum possible value that it could be if I accumulate 10,000 of these. And that's what the result type will be. And then it goes through and does that operation up to 10,000, but it can stop. What's that? Yeah, it could. And so yeah. And so what you have to do is either, if you could overflow in 10,000 iterations, then you need to do less than 10,000 iterations. It'll force you to do that. Or you could, the library implementation isn't complete here for integer promotions, but it has a big integer library that doesn't dynamically expand at runtime, like doesn't use dynamic allocation, but it can create an integer larger than 64 bits that fits the compile time bounds. Yeah. Yeah. So the question is, am I planning on doing a runtime bounds version? And the answer is basically no. I'm really sorry. Yeah. Yeah, I have thought about that too, and I like the idea of a policy for like saturation or for a wraparound because sometimes that's exactly what you want to do. And I don't have a built-in policy to do that, but you can effectively do that by using clamp and by using module operator or a bitwise and operation to force it to wrap around. Yeah. I've thought about it. I haven't thought about what it actually looks like in the design. And so I very much like the operations themselves being very explicit about what's going to happen versus that information on the behavior being encoded in the type itself. So, yeah. Okay. Hmm. Yeah. Yeah. So I've linked that here, and the are his runtime checked or compile time? I don't remember. Yeah. Yeah. So I've looked at that one. I've also looked at safe numerics, awesome libraries. Um, I have very particular ideas on how certain things should be done for our own code base. What's that? Absolutely. Yeah. Hmm. I haven't seen those. No. I should take a look. I mean, I think that would be nice to have. I don't think I've been as rigorous enough to get there yet, but at some point, yeah, they wouldn't let me get away with what I have right now. Okay, cool. Okay. Yeah, I have to put in a lot more work, but my lazy excuse won't cut it. Oh yeah, 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 yeah. So in my initial implementation of this, I had a special case where I'm like, oh, I know what the range of this is. I know it's always going to be this. So, oh, and this comparison is always going to be false. But you know what? The compilers already do a really good job of that. So I actually tell the compiler in using like the sum intrinsic or something. I tell the compiler this value is guaranteed to be within this range. Like it's guaranteed to be greater than zero, greater than or equal to zero, and less than or equal to zero. So yeah. Oh, I see. Yeah, yeah. So that reminds me of of an additional enhancement that I want to make. So here I have functions that are taking in a specific type, right? It's taking in a specific type. And so even if you have more tightly constrained what you're passing into that function, within that function you lose it, right? And so this kind of indicates to me that there's a concept version of this. So you don't lose that additional, constraint. You can pass that constraint to your calculations inside the function, and then your result will even be more constrained than it would be otherwise. Um, I love all your questions, but we only have a few minutes left, and there's two more people. So, okay, thank you. I mean, oh, I don't know how they did that. I'm assuming they had an incredible amount of telemetry and then forensic analysis, and they figure out, well, this is what it must have been, right? So with this library, um, the the only runtime check that you get is safe match, right? And so when you have some value coming in, you can use safe match to check it and kind of sanitize it, and then it'll, you can do your work within here and call additional functions, right? Or you could sanitize it and return a safe value. But if you return a safe value, then even your default has to return a safe value. So you have to know that there's a safe way to do that. But this is the default. So if it doesn't match any of your safe requirements, it's up to you how to handle that. And that's at the ingress point, right? So at least at the ingress point, there's a lot fewer opportunities. Like the surface area is smaller for things to be invalid. And usually there's better defined ways to handle that. But you could throw an exception. You could log an error. You could just say, well, we're not going to do this flow because this is invalid, right? Oh, yeah. So it does a linear search. Yeah, it checks each one. It says the question was, what's the algorithm for finding which one of these options matches the input? Yeah, and so right now it's a simple linear search. It does the evaluation for each one in order, and it's like if else. right? So the first one that matches wins. No, it's left open because you might explicitly want that kind of behavior, right? It's explicitly if else. Maybe not. I don't know. It's yeah. So the information is available for the library to potentially do that check. I'm not sure it's always what we want to do, but it could be a policy. What sounds important? DIV. Yeah. No, I didn't do those. Yeah. 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 Thank you. Thanks, Walter. Cool. So if you're interested, please check out the GitHub, Intel Safe Arithmetic. There's documentation there as well, along with some proofs. And I use quotes for proofs because I'm not a mathematician and I hope they're correct. So anybody knows better math than I do, please take a look at them. Oh, thank you, Ben, for asking. Um, the license is the Boost software license. It's, yeah, alrighty. Thank you, everyone.